Okay, so this hopefully is a fairly short video that's also looking at the value of K, but in this case we're actually looking at whether we're at an equilibrium, whether the value of K indicates that the system is at equilibrium based on concentration. So when we do that, we don't actually calculate a value of K, we calculate something called the reaction quotient, which is given the symbol Q. So I will give you a bit of a warning. There's quite a bit of text to begin with this video, so I'll go through the text first, and then I do have one example to show you. So let's start looking at this text. Okay, so the reaction quotient Q is the same as the equilibrium constant, at least in terms of the expression. But the idea here is that we're not sure if we're at equilibrium. So the concentrations or partial pressure we're dealing at are calculated before a system reaches equilibrium. So how this is sometimes used is to determine whether the system is at equilibrium based on the value of K. So the expression for the reaction quotient looks like that used for the equilibrium constant, products over reactants like you've seen, but Q can be calculated from any set of conditions, not just equilibrium. And as I said, Q can be used to determine from which direction we will shift to reach equilibrium. And so this is important. Remember, if K is greater than Q, a reaction will proceed forward. That is to converting reactants to products. If K is less than Q, the reaction will proceed in the reverse direction, back reaction, converting products into reactants. If Q is equal to K, the system is at equilibrium when Q equals K. Okay, so keep those few things in mind. We're gonna see how that works in a minute. Bit more text coming, so don't freak out. So in order to determine Q, we need to know the equation for the reaction. We need to know the quantity of Zeke species, that is molarities or partial pressures, and we have to have those all measured at the same instant in time, because remember what we're looking at here is the system at equilibrium based on concentrations at a given point in time. To calculate Q, you write an expression for the reaction quotient, which it would be the same as the expression for K, with the exception that you're not calculating K, you're calculating Q. You find the molar concentrations or partial pressure of each species involved if you need to, and you substitute those values and solve. And remember, if Q is less than K, the reaction is not at equilibrium and will proceed in the forward direction, formation of more products, to increase the value of Q to approach K. If Q is equal to K, the reaction is at equilibrium. If Q is less than K, the reaction is not at equilibrium again, and it has to proceed in the reverse direction, formation of more reactants, to decrease the value of K decrease the value of Q towards K. Okay, so here's our example. We have 0.035 moles of SO2, 0.080 moles of Cl2, and 0.0500 moles of SO2Cl2 in an evacuated 5-liter flask. So the reaction is a decomposition reaction. There it is, SO2Cl2 decomposing into SO2 and Cl2. That is balanced as written, and the question is this reaction at equilibrium? So we write an expression for Q. Q equals, so this is identical to what you would see as a K expression, equilibrium expression, but we're not sure if we're at equilibrium. That's the question. So it's still products over reactants, but we give it the designation of Q, the reaction quotient. All right, and then we substitute. Now, don't forget 0.035 moles in 5 liters. So we have to do a mole calculation there. So 0.035 divided by 5 is 0.0070 moles of SO2. 0.080 moles of Cl2 equates to 0.016 molar Cl2, and 0.500 moles of SO2 Cl2 equates to 0.10 moles of the product, the reactant. And so when we solve for this, we get a value of Q equal to 0.0011. Okay, so right off the bat, Q does not equal K. There's K, 0.0780, and we can go as far as to say Q is greater than K. Oops, sorry. Q is less than K. And so that gives us our first answer. The first bit is this reaction in equilibrium? And the answer is no, because Q does not equal K. So, just to extend this a little bit, which direction will your action proceed in order to establish equilibrium and explain your reasoning? So, let's just quickly get this information straight. So, our value of Q equals 0.0010, and our value of Kc was, I can't recall offhand, 0.078. Okay, so we already said that Q was less than K. So how do we increase the value of K? Well, remember, K equals products over reactants. And so to make K bigger, we have to make products bigger. We have to make the numerator bigger. So to do this, the reaction, so this is the explanation, reaction must proceed to the right. That is product formation. And reactant utilization. And if you do that, when you increase the concentration of products, increased products, and decreased reactants, I think you will see, equals increased value of Q. And so that's what we're going to do. So the reaction will proceed to the right until it reaches equilibrium. That is, until the concentration of products gives rise to a reaction in the back direction that is equal to the concentration of reactants being used in the forward direction. So that's one way we can utilize concentrations that we do not know are necessarily equilibrium concentrations. We calculate a value of Q and we compare it to a known value of K. And that concludes this video.